So today's lecture will be pretty short, other than, well, this part of the lecture will be short because we're going to talk about NoSQL, which is not really required for the assignments, but we'll just be talking about it because I think we're at the end, or almost at the end of like the assignment. So it'll be this one, and then we'll have one more after for deployment, and then it'll just be hack challenge. So yeah, so PA5 will be due next Sunday. It's going to be like very, very minor changes from PA4, and it's mostly for like people who didn't have time to work on PA4 or like were struggling on it. So we'll mostly be looking for correctness from that. And then coming up in the next few lectures, we'll have deployment next week, hack challenge, or like the hack challenge in, I guess, like the overview in 2 weeks. So that'll just be like people from all three of the classes, so iOS, design, and backend will be here. And then you guys, I'm not sure exactly what it's going to be, but I believe it's going to be like team matching and like figuring out the logistics. So then after that, we'll have authentication as our last like real topic, and then the last, I guess, like lecture will just be like career and Q&A that you guys might have about whatever, or app dev stuff, or classes, whatever you guys want, basically. Does anyone have any questions before we move on? All right, great. Okay, so what can we do so far? So we can have routes to receive incoming requests. We can use databases for large-scale information storage and retrieval. So we've only covered, I guess, like SQLite, but a lot of the things that we apply when we work with SQLite, we can use with more industry-level SQL databases, for example, like Postgres, MySQL, stuff like that. And then we can have, we've also learned how to use an ORM so that we have an easy-to-use code interface with the database. So some problems that we still have with our current version of things is that we still have a lot of duplicate logic. So this is the code from the demo that Megan went over last week. So we have the same logic in every route to fetch a task by ID. If we look more closely at one of these functions, we have like the code over here is like duplicated. So we get a task and then check if it's not none, and then we return that. And then if we go back, we have that same logic like over here, right? Like we have in all three of those places. So for example, like that's something that we should factor out, but it's not really clear where we would put a function like that. Like would we just put that in routes.py, or so yeah. So we have some refactoring that we want to do. We can move some logic out, but it's not really clear where to put that. So continuing with that, so our routes can end up being really bloated. So if we made more changes and more improvements and add in more features, our routes would be receiving requests. They'd also be querying the database, possibly adding or removing entries in the database, and sending a response back to the client. So I don't know if you guys have ever heard of this, but we want to basically be writing dry code. So I think it's like don't repeat yourself. That's what it stands for. You never want to repeat yourself when you're writing code. So like, for example, back over here, if we, for some reason, we changed the field name from like task underscore ID to like something else, we would have to change that everywhere. So yeah, that's basically why we don't want to repeat ourselves. Okay, so one of the things that if you're taking the iOS course, or you might have heard this elsewhere, is MVC. So this stands for Model View Controller. So we have a cool little graphic that I found. So like you have your you go like go on your browser, and then it goes to the routes. So that's like our routes.py, and then the routes are handled by the controller. So for us, the routes and controller are kind of the same thing, and then our model would be like db.py, and then that hits the database. And we actually don't really have a view because we don't, since we're an API, or like we're designing an API, we don't really control how the client actually sees it. But if you think of like if you're working with a full stack with like something like React or Angular on the front end, that's where the view logic would go. Does anyone have any questions about MVC? Like who here has heard of MVC before? Okay, so like half the people. Okay, cool. So something that kind of works better for backend development and something that we've used in the past on AppDev is this thing called the three-tiered architecture. So there's the presentation layer, which we don't really interface with, and there's the business logic and like data access layer, and then there's your data. So I have a sort of not a live demo, but like a example of what this might look like. So under AppDev, we have this repo called Register, or we still have it actually, and it was designed to be a logging solution for our apps. This ended up being deprecated, but the code in this sort of followed the same format. So in here we have like models, so we have our application. So kind of the flow was like users could sign up and then they would register an application and then they would be able to log events. So an event is defined by an event type. Application corresponds to like eatery or transit or something like that. So here it's basically similar to the stuff that you guys worked on, except with way more fields and a little more complicated functions, I guess, in terms of like init, serializing. We had some password validation, stuff like that. And then here's some session code for authentication. I don't know if you guys can actually see this, so I'll zoom in. But so if we followed this the way that we went over it in class, we would probably have our controllers, sorry, for the, 1 second. So here, like we might have a controller. So this is not with, oh no, this is with Flask, but it's with a different way of defining the functions. So instead of using a wrapper for a function, we define classes for each one. And we have handling for the route. But if you look at this, like this wants to create a user. Instead of interfacing directly with the user object, this is interfacing with this thing like users underscore DAO. So this is the data access object. And we define that over here. So this basically specifies a lot of the helper functions that we might have duplicated in other places. For example, in the slides, like this code for getting a task and then seeing whether it exists or not, like that code is right. Well, I don't know if that code is actually anywhere here, but stuff like that would be in this file basically. So sort of like an intermediary step. So if we go back to the slides, we have the data access layer, or like in our case, we call it like the data access object. So we would have a user model and then like a user DAO, a user data access object, and then we would have like the appropriate controllers or routes for each one of the routes, I guess, that the client might want. Does anyone have any questions about that? No? Yes? No? Okay, nice. Okay, so continuing on. Let me see. So you might hear this and go like, oh, what's the difference between like MVC or three-tiered architectures, all that stuff? And ultimately, it doesn't really matter. They're just concepts to guide you as a developer. A lot of the other things that you might hear, like, I don't know, like even like APIs, it's just a way of structuring your code so that a server and a client can communicate with each other, right? They're just like concepts to help developers and like help them do what they want in an easily understandable manner. And that's sort of what MVC and the three-tiered architecture also do. And some takeaways, I think it's important to, yeah, like you should separate code in whatever way makes the most sense. Like just because you've learned about MVC or learned about some specific architecture in one of your classes, if like the use case doesn't fit that, then you shouldn't do it that way, right? Like for example, if you had one of the apps that we work on in our class, like for example, like the task, the to-do list app, there's no point in decoupling everything into its own files. Like for example, here we have a file per controller. We have a file per like object. Even over here, when we define our models, we have like basically a file per model, and generally decoupling stuff is good, but then if your app is really small and self-contained, there isn't really a point in doing that, and decoupling things too much can actually make it unreadable as well. So yeah, so it definitely depends on your use case. AppDev backend, we generally use three tiers, like a three-tiered architecture, and yeah, so our data would normally be the SQL Alchemy models with something like Postgres or MySQL on the back end. For you guys, that would be SQLite. The logic is just the DAO with some queries to the ORM, and the view is the Flask API and the routes themselves. Anyone have any questions about anything so far? Okay, great. So we're gonna get into something more complicated. So this is complete. You're not like gonna have an assignment on any of this stuff. We also won't have a demo for the class today because it's the same the assignment is just from the same concepts as the last assignment. So we're gonna be talking about NoSQL. So okay, so before we start, okay, so far we've covered SQL. So like we can kind of write this out as like, so we have SQL. And this is, does anyone know what SQL stands for? Any ideas? Yeah, what's up?
Structured query language.
Yeah, structured query language. Whatever, structured query language. And then, but generally when people talk about SQL, they're actually referring to like SQL databases. So they might be referring to something like Postgres, MySQL, and there's a bunch more. So it's pretty confusing. So like for the rest of this lecture, whenever I say SQL, it's going to be referring to SQL databases and not the language itself. And similarly, NoSQL is used to not define like a language that is not SQL, but like a classification of databases that don't fall under the SQL databases like umbrella basically. Okay. So how many people here have like heard of NoSQL at all ever? Okay, great. So before we get into it, we're going to be talking about something that SQL databases have. So there are these things called like ACID properties. So these are things that like the traditional SQL databases all support. So we have A for like atomic. So every transaction is atomic. So for example, if we had like a select query, like select, say we have like a select, and then on the select, we want to perform an update. And for us, like this transaction sort of seems atomic. Like we select some stuff and then we update on it. And maybe we update multiple fields, right? But on the database side, it's not really atomic, right? Like the database has select some stuff, and then for even field updates, it's updating the fields one by one. So in terms of like this atomic definition, it means like this entire transaction, like either the entire transaction happens or the entire transaction doesn't. So it'll never happen where like, oh, we want to update two fields and then the first field got updated, but the second field didn't. And like the database just crashed or something. Like something like that will never happen. The C is for consistency. So database variants are always preserved. So like, for example, we can think about SQL as like an interface, right? Like, oh, if we say that a field is not null, then it should never be null, right? But while the database is performing some like intermediary operation, maybe it's null at some point, right? But basically what consistency says is that database variants are always preserved at like the beginning and at the end of whatever operation it might be committing. For isolation, so concurrent transactions work the same way they would in order. So a database like Postgres might be receiving like thousands of requests at the same time, and they all might be updating different objects. Basically, even if they happen concurrently and it's optimized by the server itself so that all the transactions can happen at the same time, they should, like the end result should be the same as if they were performed in order. And then the last one, durability, is, oh yeah, so if you update some field, even if you have a power outage, something bad happens, those transactions that you committed should stay committed. Okay, does anyone have any questions about this stuff? So this is all stuff that SQL databases, like, or properties that all of these SQL servers have. Okay, so, oh yeah, oh sorry, yeah. Yeah, so for example, like if you had a select and then you wanted to update two fields of an object, right? All the objects that you selected on. So for us, that transaction is like atomic. We write one thing and then we send that to the server and then we expect both of those things to happen, right? But then on the server, like on the implementation side, that might not be the case, right? Maybe it selects everything and then updates one field and then updates the next field, right? So even though on the server side, it's not atomic. Like for us, if we see that transaction as atomic and we send it, either the whole thing should not happen or like everything should happen. Does that make sense? Yeah. So it'll never be the case where you want to update two fields and then only one of them gets updated. Either both of them will get updated, none of them, and like there's some error thrown. Yeah. Okay, so with regards to NoSQL, so NoSQL databases, there's this thing called the CAP theorem, and it's also called Brewer's theorem. And there are three properties that it talks about. So there's consistency. So if you write to a server, then every read that follows that write should either receive that most recent write or it should get an error. So for example, if I go on Facebook and I post something and you are on the other side of the country and then you like refresh your newsfeed, either you should see that I posted something or you should get an error like, hey, your network connection's down. There's also availability, so every request should receive a non-error response. I think that one's pretty self-explanatory, so like every request that you send to the database should not error. And then there's this thing called partition tolerance, and we're going to get into partitioning a little later. But basically, the system should operate whether or not an arbitrary number of messages are dropped. So this means like, so let's say we have a distributed database that like runs on like 10 different servers. If one of those servers goes down, the system should continue to operate. Like there should be no like system outage across everything. Okay, great. And then there's this sort of helpful or not helpful diagram. So this is, so basically the theorem states that NoSQL database or like distributed databases in general can only satisfy two out of those three things. So if we look, RDBMS, which stands for Relational Database Management Systems, so Postgres, MySQL, stuff like that, those satisfy consistency and availability. So you're guaranteed that they'll be available every time you write to it and then you read after, you'll always get that result. But then for like C and P, we have some NoSQL databases, and then same with A and P. So we're going to get into more stuff. So talking about computers, right? So how do we even get to this point? Why do we even get SQL in the first place? So originally computers, super expensive. Like you only have like supercomputers. Like I don't know if your professors always talk about like, oh, when I was in school, like we only had one computer and like everyone had to like punch their code on a card and like that was it. And like everyone is so lucky now to have their own computers. Well, that's basically how it was. It was the same thing in companies, right? Like companies couldn't give computers to everyone. They had a few like computers that were considered to be like supercomputers at the time. But then now it's completely different, right? Like computers are really cheap to manufacture, but then like the supercomputers that we might have now are really expensive, right? And it's to the point where it's like we can all have our phones with, I don't know, really strong processors, like much stronger than like 20 years ago or something. But then the level of like computing that we can possibly have is like, it's just way too expensive for any company to realistically pay for. And so we can look at like a case study. So this is actually like highlighted on the wrong thing, but DigitalOcean is a provider of like servers. So something like AWS, DigitalOcean, there's also like Google Cloud. So if you like look at the very top, you can get like a 1 gigabyte, so a server with like 1 gigabyte of memory, one virtual CPU, some disk storage, and then you can get that for $5 a month. But then if you look all the way at the bottom, you can get something for $80, so 16 times the price. You get 16 times the memory, but then you only get 6 virtual CPUs, right? Like it's significantly less. And this is sort of what servers and like server costs really look like. Like paying for a lot more memory and a lot more CPUs gets like exponentially expensive, while we can have pretty cheap servers running for really cheap, and that's way cheaper in the long run. So having something like one SQL server for all the data that you want to have is basically like not feasible. Does that make sense? Okay, so continuing on, we have, so on the consumer side, like what do we value, right? So these are like the three things that we value now as consumers: availability, reliability, and speed. So when I go to Google, I expect Google to be there. When I search on Google, I expect the relevant results to show up. And there's always like that little thing, like we can look at it. Like if I search something on Google, like hello world or something, great. There's that little thing on the side that's like, oh, this search was, oh wait, did they, oh no, they still have that, okay. They have that thing where it's like, oh, they have all these results and it's like so fast, right? And this is something that's basically across like any platform. You never expect to have like latency at all anymore. And so SQL, when it was originally developed, was developed for those specific use cases. So in the use cases where you have like only a few computers that are basically supercomputers, and so these are like the three pretty mainstream famous ones. You have Postgres, MySQL, you have Microsoft SQL Server, which is the earliest out of the three. And yeah, so these were designed to be run on those huge supercomputers rather than accounting for what computing would look like 30 years from then, which is now. And that's basically like distributed computing, which is what NoSQL tries to solve. Any questions up to this point? All right, we're doing good so far. Okay, so what are some disadvantages of SQL? So one of the things that we stress a lot is like, oh, it's so great to have our data normalized. The thing is, sometimes it's really annoying. So especially with like all these, I think it's like been a very recent trend that like data changes extremely quickly, right? Like especially with big data and all these different things that are happening, like companies realize that they actually need to constantly change the metrics that they might store on a user or something, right? Like Facebook stores like billions, I don't know, some like tens of thousands of data points per user. Like it would be really inconvenient for them if when like Mark Zuckerberg came up with Facebook, he like forgot to include all those data points and they weren't able to update it because updating fields in SQL is really costly, right? So for example, if we start on the left, we're trying to add a new field and our database is in production, we have like millions of users already. This is really costly. Like we have to have some sort of downtime where we can perform all of those transactions because like if the server tries to query basically and detects like a mismatch between what was expected. So for example, in SQL Alchemy, say we define the thing on the left, we want to convert to the thing on the right, and basically SQL Alchemy cannot contact the server while we're updating it. Or else it'll be like, hey, what we expect is completely different from what the server has. Like the server has a middle name field. There must have been like a desynchronization. So therefore, like we're not even gonna finish the transaction. Like we're not gonna read the user's info, right? So doing something like this is really tricky, and even doing it in reverse is also tricky as well. Like it's really hard to add or remove fields given that you already have a lot of data that you're working with already. So one solution to this might be using key value stores. So this solves the issues of like having a lot of nulls when we add fields. Like for example, even here, like we might want middle name to not be null, right? But then we can't really solve that because then we would need all of our users to have values, which they don't because we're changing how the data is stored. So like there's a lot of like use case issues. Like do we require that all users fill in a middle name after saying that like we didn't require it on initial sign up? So with key value stores, this sort of solves some of the issues. We can easily update the schema. The values have internal structure that the database doesn't care about. And then, for example, in our to-do lists, like we can actually store those as a key value store. So even though it might not seem very intuitive, like whenever we're looking at a task that we have to complete, we're always querying by ID. So it's like we have a key, which is the ID, and then we query everything based on that, right? So sort of how we did it in our original like P1 where we had a global variable, you can think about it in the same way. So this was such a prevalent problem that a lot, like here are two really famous solutions, or not famous, the first one isn't as famous. Redis is pretty mainstream now. LinkedIn came up with this thing called like Project Voldemort that was basically a big distributed persistent fault tolerant hash table because they realized that they wanted to have a distributed solution that didn't really exist. And all of their data, or most data, if you think about it, can be stored in like key value pairs anyways. Like, oh, I go on Amazon. I want to look at the details of a product, right? Like if you look at the URL, like there's some ID for it and you're always querying by ID. You don't have to query on all these different fields. Like it seems nice to have and SQL lets you do that, but then most of the time you're never running those queries anyways. So Redis is something similar. I think Redis is Apache open source and that also was developed in 2009. So this is an in-memory data key value store. And some of the things that it has is like built-in replication, which helps it be distributed. this thing called LRU eviction. So basically, if your cache, if the key value store only has like 10, a storage size of 10, since it's in memory, it'll look and so let's say you have 10 and then you want to add a new item, it'll kick out the last recently used item. Does that make sense? And some of the other stuff it has is like on-disk persistence. So even though it's in memory, if your server shuts down and then it reboots, then you can still rest assured that or your data will still be there basically. So for Redis, how is it in memory but persistent? So this is actually, I don't know if you guys will find this interesting, but basically for every single transaction that Redis handles, it's appending it to the end of a file. So let's say, so Redis is just a key value store. So let's say inside of Redis, we are storing like the value for a counter, and our counter has value 0. And this is being stored in memory. So wait, does everyone know like what it means to be storing something in memory? Instead of writing it to disk, it's just like running in your RAM, basically. It's taking up your RAM. So we have a counter of 0, and then let's say a user wants to update that. So it's going to log it, say like, oh, user performed this operation, like plus equals 1. And let's say we perform that operation 10 times, right? So counter plus equals 1. And then at the end of the day, our counter has a value of 10. So it stores this in like a log file. It's not written in like English, but some sort of value, some sort of like format that's really tiny so that it doesn't take up a lot of disk space. And then, so let's say it has this, it's storing in memory that counter equals 10. And this is on your server. And then your server goes down. So it went down, it reboots, and then Redis is like, oh, let me just look at the log. And then it's able to replicate everything that already happened. So one of the problems with this is that, so that's the append. The AOF thing stands for append only file. So it's just appending transactions onto there. And then, so if you look at this, you might be like, oh, this is really inefficient. Like we could just have one log file with only one entry that says like counter equals 10, right? So this is actually what Redis does. So like periodically it rewrites the entire file and compacts the history as much as possible, so you're not using that much disk space. And then to be even more secure, you can write this to some external thing like S3, which is like Amazon's storage system, basically. Or you would write this to some sort of external storage that lives off the server, and this guarantees that your data persists. Does that make sense? Does anyone have any questions about Redis or anything else we've talked about so far? Okay, well, moving on. Okay, so some use cases for Redis. Redis, you can use it as a general purpose cache. One of the other use cases for it is using it for user sessions. So rather than storing sessions on a user's device, you want to have that stuff be on the server. So let's say in the case of like Google, which has tons of servers, I might go to google.com and it hits one server, and then I go to it again and it goes to a different server. We want to have that session. So for example, if I logged in on the first server, we want to have that session persist across all the different servers. And Redis, since it's a distributed solution, sort of allows you to do that. And there's this thing called Redis cluster, which is like the technology that allows it to be distributed. And we're going to be talking about how you can have distributed technologies very shortly. So, okay. So the last thing, one of the other problems that SQL has, or the biggest problem, is scaling. So if we think about it in terms of like, if we have like a case study, right? For Amazon, we have millions of customers, servers spread all over the world. We want servers to be performant, reliable, focused on scalability, and at such a massive scale, we don't really need to focus on those properties. Like we can sacrifice missing a database transaction, like, oops, we failed to complete your order. Please try again in 5 minutes. Like we'd rather have that than the user being unable to access the site for 5 minutes, right? And that's something, if you like think about it, it happens a lot. Like you go on Facebook and you try and post something and they're just like, oh, something went wrong. Like please try again in like 5 seconds or something. You try it again and it works. And like you don't really think about that. But if Facebook were to just like not appear for 5 seconds and your data didn't load at all, you'd be like what's going on? Like that's so much worse, right? So Yeah, and then one of the other things that's related to scaling is that they realize like most of our data can be stored with key value pairs. Like our user lookups, we can just do that by ID. Like if we want to do a product lookup, just do it by ID. Like when do we ever care about the comments on a product with like rating over something, right? Like we can just sacrifice and say, you know what, we can just store it with a key value pair and avoid having like a SQL interface at all. So this was actually a problem faced by a lot of big companies. Facebook came up with a NoSQL distributed database called Cassandra that they use. Amazon uses DynamoDB, and they published a paper on it, I believe, in like 2006, and it was released to the public in 2012. Google came out with Bigtable, which they use, and all of these relate to the problems that we've been talking about. Like you want to store a lot of data, servers are expensive, and storing stuff in like SQL just doesn't make sense when you have so many constraints. Okay, so we're gonna focus on DynamoDB. I believe Amazon was like the first to actually publish like a paper on like how you might have a distributed database, and so we're gonna be focusing on that. And some lag, but so DynamoDB is like a paper that you can read about. I think it's only like 8 or 10 pages. It's pretty short actually, but it goes over a lot of important concepts. So they kind of justify it as they have this problem where they want an always-on experience at Amazon. They said in the paper, like at the scale, small and large components fail continuously, and the way persistent state is managed in the face of these failures drives the reliability and scalability of the software systems. And in general, throughout the paper, there's this notion that they were willing to sacrifice consistency for very, very high availability. Okay, so some of the stuff that was super new and really innovative was this like ring-based architecture that we're going to go into. We'll also be talking about smart partitioning with consistent hashing. So it's okay if like none of this makes sense, but these are sort of like the concepts from DynamoDB that we're going to be talking about. Okay, so the first, does anyone have any questions?
On an earlier slide, you said that
Yeah.
like these new systems don't focus on the asset properties.
Yeah.
So like, how does that work? Like, if let's say for the atomic property, like you try to update something, and it does one of the updates but not the other one.
Yeah. So
Then
in like so they came up with a lot of different terminology to like so it doesn't satisfy all four like completely, but generally like for the atomic one, that one's important enough that they'll always preserve that one. And in terms of like consistency, they define like strong consistency and like something else like eventual consistency, and they define their own rules to make sure that like important transactions always were committed, basically. Yeah. Does anyone have any other questions? Yeah, what's up?
So like does any like I guess large scale company use SQL databases or not?
So SQL is still used, but not like in terms of like big data that needs to scale or like could scale like to an enormous level. Like there isn't really a use case for it anymore. And so like SQL as a language is still around, but like the single server architecture is just pretty bad because SQL doesn't really come with support out of the box. Like it wasn't SQL servers and like SQL databases weren't designed to be distributed, right? They never saw the need to like have 10 different databases with like the data being split across all of them. So generally like these solutions are used. And they also like still support querying. So it's not like they threw querying out the window. It's like they took some elements of like the language, but then the architecture like of how the databases are actually working is completely different. Yeah. Any other questions? All right. So we'll get into the first one of like the points. So one architecture that's pretty common when you have like distributed systems is this like manager worker architecture. So you might think about this as like, I don't know, like you're in a class and then someone is teaching the class. So it's like, or in like a workplace setting, you have like manager and workers. So like the manager knows what's going on, assigns work to all the workers. Workers just complete their tasks. But this is actually not that good because you have a single point of contact and it's centralized. Like for example, if So this is an example with like Docker Swarm, which is something we'll get into next lecture, but follows the same architecture. So you have like the Swarm manager and the Swarm workers. But if the manager node was to go down, it's like unclear. Like then we have to, if you think about this from a coding standpoint, like does one of the workers get promoted? How do we choose the worker? Like what if the manager had information that none of the workers had? Like how does all that get handled, right? So they chose to have a decentralized architecture that was like ring-based. So before we get into that, we're going to talk also about partitioning. So partitioning is basically taking the contents of a table and then splitting it across different servers. So for example, if we had, let me see, what is this actually? So let's say we had a table with regions, and then you might choose to partition it by like, oh, maybe I don't know if this is Great Britain, but like maybe Great Britain has a lot of data for some reason. We'll like split their stuff into 2 different servers, and then put each one on its own server. Like Ireland will go on its own server, and then the US will like go on its own server too. So that's just partitioning. This is really important because if we want to move from like SQL to a distributed database system, like we need to have some notion of how we're actually going to split the data, right? And some fancy words. So people might talk about like sharding. That's just what we talked about, horizontal partitioning. So like if we have a table with a lot of rows, like we have a table, then you just like cut it in the middle of like one of these rows. You like horizontally cut it, and that's just all that sharding is. There's also vertical partitioning. So instead of splitting up like rows 1 to 3 and like 4 to 6, you split it this way, and then you split row 1 up across different databases. But if you think about it, this isn't really great because, like we said, a lot of the queries that you're running are running by ID anyways. So you would have to look up on 2 different servers instead of just doing 1 server lookup. And partitioning in general, however you choose to do it, allows us to split up data across different servers. So does anyone have any questions about what partitioning is? Okay, great. So how can we partition effectively? So let's say we have, all right, so this one's going to be a little tricky, but let's say we have a IDs, or like we want to partition the data in a table, and the table, like our tables, just has integer rows. So this actually doesn't work because, well, what doesn't work about that? Does anyone have any ideas? So like, let's say we have a table, and this just goes from like 1, and then maybe it goes to like some infinity. We have like billions of users, like, and say we wanted to partition this among 3 servers or something. Does anyone have any ideas how we might do that? So we have like an infinite amount of rows, like billions of rows, and then we want to partition across 3 servers. Like any guesses? How would we do that? Yeah, what's up?
So these are sort of like some kind of ID number system?
Yeah, so all we have are like the row IDs, and there's just a lot of them. So like maybe not infinity, but like enough.
It's an amount that changes. There are more.
Yeah. So like let's say we add a new row. Like which server would you send it to? Yeah, what's up?
You could do like you could essentially loop through. So like this user you put on machine 1, and the next person that joins goes to machine 2.
Yeah. Yeah, so that makes sense. What if we wanted to partition like existing data? So like let's say we had, I don't know, 1,000 rows already, and we want to just partition by 3. We could just like modulo it, right? So we take the index and then just mod by 3. But this ends up being more tricky if we have more, like we don't know the number of machines we have. Like if we want this to be scalable, like this number is just a mystery, right? And we don't want to have to reformat everything. For example, like let's say we did the mod approach and then we added a 4th server, right? Then like we would have 1, 2, 3. So I'm just going to number like which servers they would be assigned to. But then if we added a 4th, we would have 1, 2, 3, 4, 1, 2, 3, 4. Like all of these go out of sync, right? So it's really expensive for us to allocate in that way. So something else that we might do is instead of having it go on linearly, like we can make it a ring. So we can take whatever ID we have and then run this through a hash function that gives us some integer between like 0 and n, right? And then we can make a ring like this and have this be 0, and then this will be n minus 1 or something. And our stuff will be mapped around this ring. And instead of doing it the way that it's done, or we'll do it basically something like this. So we'll place these 3 machines randomly. So like maybe we'll have machine 0 here. Sorry about the confusion in the picture. So we'll have machine 0 here, machine 1 here, and machine 2 here. And then whenever we have a row, like let's say we have row something, I don't know, it doesn't matter. We'll basically go clockwise until we find the machine, and that's the machine that we put the data on. Does that make sense? So we take all these indexes, we map them to some n value, maybe we just modulo those, and then now we have some sort of ring, and then whenever we have an access, we can just traverse the ring and get up to here. But this is still not that great. So let's say we did it this way, and then we want to add a new server, right? Let's say we add one right here. So these are being assigned, the servers, like the position that they have here is also being hashed by the same hash function. So it maps it to somewhere in the same range. So for example, like we might have just a really bad hash, and we might accidentally assign a server here. So if you think about it, like the range of requests that this new server is handling is only like this region, right? Like a much more efficient assignment would have been somewhere here, right? Does that make sense? So how can we solve this problem, right? So we have like this ring thing, and then this sort of allows us to have a clever way of assigning requests or rows in our table to different servers. But one of the things to note here is that we wouldn't have this problem if we already had like 100 servers. So let's say we had 100 servers, then we would have like points all along here. And then if we removed one or if we added one, like it doesn't matter where we put it because the circle is already populated, right? Does that make sense? So like if we had 100 of these, or like way more, then there isn't really a bad assignment. Like previously, this assignment was so costly because like the difference between this and like that was like massive. But then if we have all of these already here, and then we add one here, like you can't really say like, oh, there was a better place to put that server, right? So the way that we can do this is we can virtualize the ring. So instead of assuming that we actually have 100 servers, we have 100 like virtual servers, and then we assign all of those hashes along the ring, and then like node 0 here has like virtual servers assigned to it. Does that make sense? So like instead of having, so we can number these the same way. So we have like 0, 1, 2, 3, 4, 5 or something, and then maybe like 0, 3, and 6 are just like getting assigned to a big server 0. So let's say we have 3 servers again. We're like assigning like virtual spaces to each of the real servers. Does that make sense? Any questions? This is a tricky one. So the problem, yeah, what's up? Yeah.
We were talking about how like if the ring's already populated,
Mm-hmm.
then it doesn't really matter where we place the new server.
Yeah.
Because even if it's not optimal, it's like not listed.
Yeah, it's like, so for example, if we had one server, and then that server's here on the ring, and then we're doing it clockwise, and we assign a new server here, now this server only services like this part of the ring, while like all of this is getting serviced by this, right? But then, and if we had like a lot, like we had like 13 or something, or whatever, if we had enough, then like no matter where we add it, it doesn't really matter, because like the difference between here and here and here and here isn't that much, right? So the solution is not to have this many servers, but to like pretend that we do. And then, for example, if we only had 2, we could number these 4, 5, 6, 7, and then so on and so forth. And then like 1, 3, 5, 7 would be assigned to server 1, and then 2, 4, 6, 8 would be assigned to server 2. So this allows us to like to solve the problem of partitioning really well and have random partitioning without actually having to have like the number of servers that we want. So this is actually like a super new idea, and I think like the Dynamo paper was like the first paper to actually introduce this concept and allows you to partition really effectively. Yeah, what's up?
How do you know how many servers you would have to run as compared with how much data you have in the server?
Well, the whole point is like you want to be able to scale it. So you can have as many virtual servers as you want because you don't actually have virtual servers. Like they're just imaginary. And then the way that they get assigned to real servers is like dependent on how many you actually have. So it scales pretty well. Yeah.
So with this graphic,
Mhm.
are the colors physical servers? Is that the idea?
Yeah. So like
And
there's
it's
4
split up.
servers and then like they get split up across this ring, but it's random. So instead of having like 1/4 be green, 1/4 be orange, right? Okay. Oh, okay, yeah, so, sorry, actually, yeah, you can go first.
But when you add a new server, wouldn't you have to reassign the colors? Is that a problem?
When you add a new server,
Right. You would have to reassign the colors to each server. Now the yellow ones maybe would have to be moved.
right, yeah. So like the way it works is it happens incrementally. So like you would add like a new virtual server at first, so it would only have a small portion, and then it would communicate with the other nodes in like the system, and then slowly get other portions, basically. So yeah, so you like pretend to add a virtual server at first, and then it gets more virtual servers later. Does anyone have any other questions? Yeah.
This is like continuing from the first thing I asked. Like, even if isn't the measure of how like significant the position where you put your new
Yeah.
server on the server like sort of subjective, because like if you have a large amount of data and not that many resources,
Mhm.
like even if the ring's already populated, if you don't choose like the optimal position, it still might be like
Oh no, but like if you have a lot of data, like billions of rows, and then you have a good enough hash function, which we're assuming we do, then like the data will be evenly populated. Like this requires the data that you already have to be hashed by some hash function that randomly assigns it with like an equal distribution. Yeah. So it's not going to be like the case where like you have a large amount of data in a specific region. Yeah. Okay. So adding, removing nodes, we sort of talked about this. So one of the other things that we might have as a problem is like, how do we handle failure in the distributed system? So like, for example, if like node 0 all like lost its power, like what would happen? So the way that this solves that is like there's some arbitrary number that is like determined, I guess, at start time, and then the following. So like this node will have like these 3 copy the same data as that one. So like node 1, 2, and 3 will also have this virtual server like running under that. So that's how the data is replicated. So if node 0 goes down, like node 1 will realize and then but still be able to service the request, right? Because say like a request came here, then it would be like, oh, there's no server here, so it's going to go down here, which is node 1, but node 1 already has that data. Does that make sense? How this solves that? Yes? No? So, okay. Let me think. Is there a better way to explain this? Let's see. So let's say we have this circle, and then we have a server here, and this server goes down, right? Then it's gonna, this like arrow will continue until it hits the next server, right? So that's why we always back up, like, we back up the data from this server onto like whatever node is running that data. Does that make sense? So even if this one goes down, it'll like continue, hit the next server, and then hopefully that will have it. But then in the rare case where this one goes down, this one will also have that data copied. So in the graph over here, we have like 3 nodes that are copying the same data from A, basically. Yeah.
does every physical server like have a copy of all the data, or
No.
just like
So like the physical servers have virtual servers under them.
no,
Yeah.
But, like in the slide before you said
Yeah.
that like let's say the green one goes down,
Mhm.
and the orange one has a copy. And then
Well, it's not like in this specific, like that virtual server will be copied by the next one.
So it doesn't map to like the physical servers.
No.
So like the first green is
Yeah.
not the backup of the second.
The first green is not the backup of the second green.
Or the second green does not have a backup of the first.
The second green does not have a backup of the first green. Wait, which is the green? Which is the first and
That's
second green?
That's 0.
Well, like, this virtual server is being backed up by this one, and then this one is always being backed up by that one. It just happens that orange is always following green in the diagram, but like it could be followed by a different color.
Okay. But like, I guess I'm asking how far does that chain of backups go?
Yeah, so that's like the arbitrary constant. So like in this picture, it's just 3, but then it could be whatever number. It's like determined by Dynamo, basically. Yeah. Okay. Continuing on, so we have consistency. So consistency is the one thing that Dynamo gives up. So rather than having strongly consistent reads, so this means that like if I write to the server like, oh, I want to buy something on Amazon, and then I refresh the page, it might not always show up. And the way that they do it is like if you wait long enough, that transaction will get propagated across enough nodes so that when you refresh, you'll see it. And that's called eventually consistent. So like if you wait long enough, the change that you wanted to make will propagate across everything, versus strongly consistent, which is like what SQL has. So if you update a field and then you immediately requery it, you'll see it. And so when you have a node, okay, so let's say in this simple diagram on the left, with only 3 servers, you want to issue a write. So you want to write to some data. So first, like maybe you go over here. So the write comes in to this circle and basically finds the nearest server, and then the write to like object A is done here, right? And then a read request comes in, and then let's say the write happens here. These servers copy the data or something, and then server A goes down, right? So maybe this, it's like running in the background, like it's trying to copy all the data from A. It's like, oh, object A has been updated. This server is trying to remember that. But then a read request comes in immediately after. Maybe it comes like this, right? And then tries to issue a read to object A. Like, how do you version those changes, right? So the way it works is like changes to this server are propagated to its neighbors, and that propagation continues to happen. So maybe if we had multiple writes to the same object, like the way it works is really similar to Git. It stores like a history of every single transaction that's made. Each node stores its own history, and then those transaction histories are propagated across everything. And if there's ever a merge conflict, so like, oh, 2 computers try to access or like write to the same object, the later one always wins. There is no merge resolve algorithm. So like if I try to buy product A on Amazon, and then someone else who was logged in on Amazon tried to buy product B, and then there's a conflict between the two, the person who tried to buy the product later would win in the case that there was a conflict. Does it make sense? Okay. And the last thing is failure detection. So what happens when a node goes down? So every second, basically, a node contacts another node at random, and they exchange the histories of like the other. So let's say like this server goes down, the request now goes to this server, and this server is like, oh, now I know that this server went down, or else I wouldn't have gotten this request. Every second, some random server will ping to this server like, hey, which servers are up right now? And then they'll find out. All the servers will eventually know that this server is down. And then since it's decentralized, at some point, like there will be a request issued to like boot this server back up. So that's how it handles failure. And generally, like gossip-based failure is how you handle failure in like distributed systems, unless it's in like an architecture where it's decentralized. So for example, in like the other architecture that we went over in the beginning, so if we have an architecture like this, let's see. So the manager-worker architecture, like if we have a failure here, then the manager hears and then basically boots another worker up. And then, but if the manager fails, like you're just screwed. Like that's why this architecture doesn't really work sometimes. Any other questions? I know this was a lot. We covered NoSQL last semester, or the person I co-taught it with covered it last semester, and it's a lot. But I think it's pretty cool. You can do a lot of more research into it by yourselves. Like there's the Dynamo paper. There are like tons of like YouTube videos trying to explain all of these different concepts. But yeah, if anyone if anyone doesn't have any more questions, I think we are done for the day. All right, yeah, nice.